Power generator development. Let me make it very clear, this is just a suggested development project. I have never seen a generator of this type in operation. The design is based on the idea that feeding a high voltage to an ordinary three-phase DC motor produces a great increase in torque or turning power of the motor. This is confirmed by a developer who tried it some years ago and found that by doing this it did not harm the coils of wire inside the motor, but so much torque was produced that it broke the output shaft of the motor. Generally speaking, the system suggested here is to feed about 400 volts to a 12 volt three-phase motor. The increased torque of the motor is used to spin an ordinary alternator to generate normal mains equipment and equivalent voltage and mains frequency. Finally, some of the output of the alternator is fed back to provide the input power of the system. If a battery is used to start the system, then that battery is recharged by the feedback, even though battery power is only used very briefly at startup. The overall arrangement is like this. You have a battery which provides 12 volts to an inverter, which steps it up to 220 volts AC. That is passed through a transformer to give you 400 volts and passed to a controller, and the 400 volts is fed by the controller to the three-phase motor, which then physically drives the alternator, which produces 220 volts. That is then fed to a battery charger and other loads that you want to power, and the battery charger produces 12 volts or so, which is provided to both the battery and the inverter, the majority going to the inverter itself. The most important components of this system are the controller and the motor. You're probably familiar with the most common type of motor, which is a single-phase motor, but the more powerful motors used in industry are three-phase motors. There are several varieties of three-phase motors, but the type that we want to use is called a BLDC, or brushless direct current motor. These motors are available with or without built-in sensors which indicate the position of the motor as it spins. We want to use any sensorless three-phase motor, and those are the cheapest types of three-phase motor available. The website www.simplecircuit.com published a program which allows an Arduino Uno R3 board, that's revision 3 board of the Uno, to act as a controller for a brushless, sensorless three-phase motor. That design is on the website, and it appears to be a very successful design, and it has been offered free since January 2018. It is not necessary for you to become an expert programmer of an Arduino board, as the program used here is provided directly for you. A good instruction video on how to program an Arduino Uno board is shown here at youtube.com. Ideally, we would like the generator to be able to power any of our household items of equipment, that is, washing machine, tumble dryer, vacuum cleaner, fridge, electric fire, air conditioning unit, fan, or whatever. To do that, we would like a generator with 3 kilowatts of electrical output, and that suggests a reasonably large motor. A three-phase motor sounds very technical, but it really isn't. It's just a motor which has 3 sets of drive coils instead of just one drive coil. One three-phase motor which appeals to developers is the Samsung washing machine motor, as it has 36 different coils, and those coils are connected as 3 sets, each set having 12 windings which are connected together. Coil set 1 has coils 1, 4, 7, 10, 13, 16, 19, 22, 25, 28, 31 and 34. Coil set 2 has coils 2, 5, 8, 11, 14, 17, 20, 23, 26, 29, 32 and 35. And finally coil set 3 has coils 3, 6, 9, 12, 15, 18, 21, 24, 27, 30, 33 and 36. The motor itself looks like this here. The coils are stationary as they form the stator section of the motor. There's a continuous ring of magnets immediately outside the coils. Those magnets are attached to the metal dish-shaped end housing which spins around, being the rotor of the motor. So the motor has effectively just 3 coils in it, and it's made to go round by pulsing the coils in order. That is, pulse to coil 1, then a pulse to coil 2, then a pulse to coil 3, and then coil 1 again, and so on. The more rapidly that the coils are pulsed, the faster the motor rotates, and in this system the rotation can be very fast indeed. The suggested motor is available as a replacement part for a washing machine and can be bought quite readily. However, 2 bearings and a drive shaft need to be constructed in order to convert the Samsung motor into a device which can drive an alternator. There you can see the ring of coils. Outside that ring is a row of permanent magnets which are attached to the outside metal casing. That's bolted through to a shaft which is supported in another bearing and giving you the drive shaft output at the end. It's quite neatly constructed and shown here. Doing that precision metalwork will probably be necessary to balance the rotor to avoid vibration when it rotates at high speed, typically 3000 revolutions per minute, to drive the alternator at its correct frequency. This metalwork can be done by a local metal fabricator business if you do not have the necessary equipment or skill to do this work. For testing purposes, it might be more convenient to use a different motor to provide a proof of concept. One of these 3-phase motors from China looks particularly suitable as it's low cost and has 2 bearings on the drive shaft. One motor can be the drive motor, and a second identical motor could act as the generator. Aligning and coupling the motor and generator shafts is not difficult, and components from model aircraft and radio control car shops can be used. The simple circuit provided by simplecircuit.com for the motor drive is based on 12 volts throughout. 12 volts are fed in here and power all of the circuitry and the feedback to the Arduino. The challenge for this particular generator design is to modify this circuit so that the Arduino is run on 12 volts while the motor is run on 400 volts. Because the motor has no sensors, the simple circuit people used the back EMF voltage feeds from the motor to determine its position during rotation. And you can see how they have it fed here into a comparator. That comparator is located physically inside the Arduino board. But our problem is that we are feeding the motor with 400 volts instead of just 12 volts. So what voltage will be fed back to the Arduino? Originally, the simplecircuit.com circuit shows a resistor divider pair of 33K for the upper part and 10K for the lower part, which drops the voltage to about 1/3 before feeding it to the Arduino. But it is the back EMF which has allegedly been fed back, and that is generated by the coils. And in a 12 volt system, that feedback is likely to be very much in excess of 12 volts, and it could be in excess of 1000 volts. Pulsing the coils with 400 volts might well not alter the back EMF by very much, as the coils are not changed. This is the problem, and testing is needed using your own motor to determine what is coming back from the motor. It's suggested that the resistor divider pair of resistors be changed to 1.3 meg for the upper part and 10k for the lower part, or alternatively to 10 meg for the upper part and 2.2k for the lower part. There are cheap Chinese versions of the Arduino board, and they sell for just £5, so it might be a good idea to use one of those for the testing phase of the development. At this point in time, we just don't know the answer, so we'll have to see what the development testing shows us. The pulsing of those 3 coil sets, one after the other in sequence, is done by the controller unit, which is a key component in this design. The controller consists of 2 parts. The first is an Arduino board, which is a general purpose development board, essentially a simple computer which can be programmed from an ordinary personal computer or laptop. It holds the program in its memory, and it runs it whenever it's instructed to do so. The second part is an electronics link between the Arduino board and the motor. That link boosts the power fed to the motor using high-powered transistors which can feed high currents to the motor. And there are some other wires then which feed information back from the motor to the Arduino board to give the Arduino full control of what's happening with the motor. The Arduino code can be downloaded as a text file from www.freeenergyinfo.com/arduino.txt. The Arduino board itself looks like this. You have the main chip on the board, which contains the circuitry of the computer, and then there are support components around it as well. Then there's a row of connectors on the right hand side and another row of connectors on the left hand side. There's an access plug for providing power and a linking plug which can be plugged directly into your computer. The interface chip that we want to use in addition to this is called the IR2104 integrated circuit. The interface between the Arduino Uno board and the motor needs this list of components here. There are a number of components. They're not very many, and they're not particularly expensive. We need to connect the Arduino Uno drive to one of the 3 phases of our 3-phase motor. So to do that, we will use an IR2104 driver chip and an IRF840 field effect transistor to feed our 400 volt power supply to the motor, and we will do that about 14,800 pulses per second. So the power drive for the first phase is like this. You have a couple of connections coming from the Arduino board to drive the IR2104. There are support components including a resistor, which is a high voltage component, and the output is from pin 6 of the IR2104, and that goes via the IRF840s above and below to phase 1 of the motor, and that's one phase of the motor, which is a 3-phase motor. The IN5408 diode is a 3 amp diode which can handle high voltages, typically 1000 volts, and so it protects the 12 volt section of the circuit from the high voltage section feedback. The power drive for this second phase is pretty much identical. The difference is that there are 2 different points on the Arduino board which drive the IR2104. The minor circuitry that's in this arrangement here is unchanged and exactly the same as for phase 1. The 2 FET transistors are connected together there, and the line goes out then to drive the motor. The power drive for the third phase is pretty much identical. You've got two different connection points on the Arduino board driving the IR2104, and the circuitry is identical except that it goes to phase 3 of the motor. We also need to provide the Arduino board with feedback information to let it know where the motor is in its rotation. That is done by sensing the phase connections to the motor, and in this case we're using guessed voltage divider resistor values as shown here. You've got 1.3 meg on the upper part, 10k on the lower part. You could of course make the 10k a 20 turn preset resistor if you want, and adjust all three very gradually upwards from 0 until you get the Arduino board working correctly. But that is the way that the connections are arranged to feed the power back to the Arduino. First of all, we need to have a warning. You can get a shock from any voltage above 30 volts. If the voltage is alternating current at a frequency under 100 cycles per second, that is typically as supplied by your mains wall socket, then that shock can be serious, in fact very serious. The power supply described here is very easy to understand and to make, but if you get a shock from it, that shock is very likely to kill you. So we have a disclaimer. You are responsible for your own actions. This document is for information purposes only, and if you decide to make or experiment with voltages higher than 12 volts, then you and you alone are responsible for your actions, and neither the author, the web hosting service, nor anybody else is responsible for what you do or for any damage or injury caused by your own actions. Having said that, please understand that if you are careful and sensible, there is no danger in constructing the power generator in spite of the very high 400 volt input to this power driver circuit. To stay safe, you make all the necessary connections and insulate them before you apply power. So we need to construct an electronics component board to connect the Arduino to the phases of the motor. Please remember that this board will be carrying 400 volts, and so you need to enclose the board in a plastic box before powering it up. The suggestion for a physical layout for the components is based on using a strip board like this. It is copper strips running the entire length of the board, and there are holes spaced every 1/10 of an inch along the strip. These boards come in many sizes and are very versatile. However, because this pin spacing of an integrated is just 1/10 of an inch, the solder joints can be very close together, and that does not suit a beginner to soldering. So ask a friend for help in soldering unless you're already expert. We want to place the components of one of the phases on a board, so perhaps a layout like this might be suitable. You have the power supply coming in, 12 volt power supply, 0 volts there, and a 400 volt supply coming in here, and the 0 volt line is fed up through this jumper here to the actual FETs being used in this combination. Now the socket here, at least I'm suggesting you use a socket, has to have the copper strip broken between the pin 1 and pin 8 and pin 2 and pin 7 and so on for the 4 pairs of pins. If you don't do that, obviously pin 1 will be short circuited permanently to pin 8, so you have to make a break in the copper strip there. The red circuits here indicate where you would make breaks in the copper strips. The physical board layout shown here has not yet been built and tested, and so this is only a suggestion. You can make 3 separate boards, one for each phase, or you can place all 3 circuits on a single board. Integrated circuits are heat sensitive, so I suggest that you use a socket and solder it in place, and then plug the chip into the socket when everything is cool. An 8-pin socket looks like this. Very simple, very straightforward, and they are not particularly large because of the 1/10 of an inch spacing. Here is a possible physical layout for the interface using a piece of strip board. Again, let me remind you that this has not been built and tested, and so is only a suggestion. You have the resistor divider and feeder resistors from the Arduino, from the motor coming back to the Arduino. You've got the FET transistors positioned on the board, and you have a drive to the gate of the FET transistors feeding across there. The red circles are, of course, still breaks in the copper circuitry. You've got a press button switch here to make the thing run slower. You've got a press button switch here to make the circuit run faster. You've got 3 sockets there for the IR2104 integrated circuit board, and this is one way of connecting the components together to make the circuit operate. But in this layout it is almost certain to damage the Arduino board, as there are issues with using 400 volts. It may be necessary to introduce a high voltage fast diode to protect each IR2104 integrated circuit from the high voltage of the motor circuit. A diode such as this 650 volt 8 amp SCS 306 AHGC9 diode. It looks like this, very simple. Got 2 pins coming from the housing. The cathode is both the heat dissipation plate and one of the pins. The anode is the other pin. That's the symbol that's shown on a diagram to represent a diode of this type. The changes to the physical layout include introducing one of those diodes across so that the cathode faces the feed to the phase of the motor. That is to protect this side of the circuit from the high voltage on that side of the circuit. That is a more feasible circuit possible layout. Let me state again, this is only a suggestion. It has not been built and tested, so it is definitely only a suggestion. We come to a difficult part now of producing a 400 volt power supply able to supply about 2 amps at that output voltage. We can very easily produce higher voltage power supplies. For instance, if we connected 2 12 volt inverters together, we would get 440 volts. But we want to restrict the voltage for this circuit to 400 volts, and that is not particularly easy. What has been suggested is that you use a 12 volt battery to feed an inverter, and then use a transformer to step the 220 volts coming out of the inverter up to give you, after rectification, 400 volts DC. Some of the output will be fed back through a battery charger to the battery and inverter. But please notice that the transformer itself is not at all easy to find, because very few people want to produce 400 volts DC from 220 volts AC. The battery charger, though, needs to supply hundreds of watts of electrical power continuously back to the input of the inverter. This is to make the system self-powered, and the actual so-called battery charger here is really a very heavy-duty professional level unit, so heavy that it needs wheels and a handle to actually move it around the place. They're not particularly cheap items. You can get them for about £150 in the UK. So first we have a car battery that feeds an inverter like this, for instance. This one is a European inverter, produces around 220 volts with powers of 2000 watts continuous and 4000 watts peak output. It's also very cheap at £25 delivered, and it has two handy USB output power sockets as well. In the absence of a suitable step-up transformer, one possibility for the power supply is to use a DC chopper circuit, which would take the 12 volts from the car battery and produce a 400 volt 20 kilohertz output directly in one operation. This is a picture of one suitable board of that particular type. It's a DC chopper power supply is not suitable for all applications, but it's felt that this cheap unit, which costs only $35 from aliexpress.com, would be suitable for this generator project. However, please understand clearly that your local power supply is most unlikely to allow you to connect your generator up to their wiring, which goes into your house and connects to your fuse box. Consequently, it's better if you use your new supply of electrical power as if it were an emergency backup generator. That is, you connect it up to your appliances without connecting it to any external power supply or wall socket. Let me stress that if you were to construct a generator system like this, you do not connect it to the wiring of the local electricity power supply company. For example, the electrical mains supply wiring will come into your household fuse box or contact breaker box. Do not connect your generator wiring to that same box, but instead treat your generator in the same way as an emergency generator, feeding the generator output directly to your washing machine, electric heater, vacuum cleaner or whatever through an extension cable and not through a wall socket. If you're very keen to have your new generator connect to your fuse box, then be sure to install a break before make type heavy duty switch to disconnect the outside power supply cable before your generator output is connected to the fuse box. This is important because if a fault occurs in the mains wiring outside your house and they turn off the mains power while they go to fix it, the workmen might get a fatal shock from your generator even though their wiring is supposed to be switched off. So it's very important to keep your new generator disconnected from the outside electrical supply wiring. We come now to the alternator, which produces the electrical output, which is the whole point of the system. All of the components and methods described so far have the objective of spinning the alternator indefinitely in order to provide electrical power for a household. With the large motor, the system described so far is perfectly capable of driving an alternator of any power level up to 10 kilowatts or even more without altering any of the components. So the size of the alternator which you buy is up to you. Personally, I would consider an output of 5 kilowatts as being adequate to excessive, but then my electrical needs are probably lower than yours might be. Anyway, in the UK, one supplier of such alternators is Machine Mart, and they offer 3 different alternators. They look like this, as shown here, and they each need to be driven at 3000 revs per minute. This top one here is 6.5 kilovolt amps. Now let me explain kilovolt amps. Kilovolt amps are the same as kilowatts if and only if the load has got no capacitors or coils in it. In other words, if your load is purely resistive, like light bulbs, then you would consider this to be a 6.5 kilowatt generator. But if you're using it for normal things like washing machines and vacuum cleaners and refrigerators and the like, which have got motors in, then you would consider this 6.5 kilovolt amp alternator to be 5 kilowatts. This particular one is offered in 2019 at £324. There's a smaller one at 3.5 kilovolt amps, but it costs £288, which is not a lot of difference to 324. The smallest of their types is 2.2 kilovolt amps, and it's at £240, which is less than £100 lower than the price of the 6.5 kVA device. If you're going to use pulley wheels, then you can get them for about £15. Looking at the small price difference between the alternators, there seems to be very little reason not to pick the 6.5 kVA unit, even if your expected current is likely to be well below that rating. If you limit the output current to your own load to say 3 kilowatts using a fuse or a circuit breaker, then you can install a higher capacity alternator. That will not increase the load on the motor, as the alternator is always running at less than its design current. The alternator will not create a greater load, and it will run cooler. The final step is to mount the motor unit and alternator unit together so that the motor can drive the alternator to provide the required electrical output. Aligning the shaft of a large motor with the shaft of an alternator is not an easy thing to do unless you are skilled at such work. For the average person, it is easier to use a pulley wheel on the motor and a pulley wheel on the shaft of the alternator, linking them together with a belt drive, as is done in a car. That is the effectively easier way of doing it. You align the alternator very carefully with the motor pulley, and the belt drive then will work quite adequately. That is the general outline of the design of this particular generator system. It should be remarked, however, that as development is continuing, if we find out additional information on resistor divider pair values, position of additional diodes or whatever, then this document will be updated at a later date. So it's worth keeping an eye open for this particular document, which you can download free at any time you wish.